Welcome to my Causality talk. I'm delighted that you have decided to learn more about causality. This will take about an hour or a little bit more, but it's time well spent because causality, according to a bunch of philosophers, is the most important relationship in the universe because cause effect relationship determined according to one school of thinking. Now, the topic is very broad, so I will constrain it to in the context of IoT, Internet of Things. So I got interested in causality about 4 to 5 years ago when I spun out a causality startup from NEC. NEC Labs had done some pioneering work in this area of causality. But even earlier, I've been very well aware of the cause effect issue while working at Rockwell Automation, which is a machinery monitoring company. The IoT and digital twin solution that my team developed, we saw that the work never stops when IoT detects a fault. The experts get together on the plant floor and then do what is called a root cause analysis inevitably after such an event. So root cause. So they want to find the cause. Cause is always what drives this to the next step in IoT. Even before that, when I was a faculty member, my work was in neurophysiology and computational neuroscience. And when we measure signals from the surface of the brain outside on the scalp, that is never the end interest. Our interest was always in what's going on inside, what is causing these signals to appear on the surface of the brain. That's called an inverse problem. So these are the things that has always kind of uh, driven my interest in causality. Now, to relate causality to the IoT, let's look at the business aspects of IoT. Many people, including me, think that IoT is in a bit of a trough of disillusionment. There were many early successes, a lot of sensors and connectivity and display digital twin and all those beautiful pictures. But there is a sense that beyond these nice dashboards and pictures, there isn't a lot of operational value being derived from IoT. And my diagnosis of the situation is that, so far we've been treating symptoms. We need causality to start addressing the causes, such as root cause we talked about, or saying, if you do this, the performance will improve, so-called prescriptive analytics. This requires causality, cause-effect relationships, and we are at that stage where we are hung up, in my opinion. So let's take a step back and start from basics. Uh, Correlation, causation. There is always this joke about correlation is causation, and there is almost an implication correlation is somehow inferior, perhaps, to causation. But we'll see. Is that really so? So here is a study where measured if you've gone up a mountain, at higher altitudes, temperature seems to fall. Right. So they made it with a lot of measurements. These are all these dots and fit the regression line. So it's kind of useful. But while doing it, you know full well that causality. Air temperature is not causing altitude. It's altitude causing the air temperature. But correlation is not totally useless. Say you're going up on a mountain retreat somewhere around 2,500 meters. It's going to be around 12 degrees Celsius. You better take a good jacket. Uh, Instead, you decide, oh, I'm going to go up to Tibet, which is 4,000 meters or so. So, yeah, I better get a parka with some goose down stuffing and all that. Now, let's say you decide you're going up to Mount Everest. Mount Everest is about 8,000 meters, so it's way out here somewhere. Now, this is where correlation, you should be careful. If you extrapolate and decide that is what you should be wearing or using this as a guide, you're probably going to be totally wrong because the extrapolation ability of correlation is non existent. So, what do you do if you have to proceed further? Well, you could always go to NOAA, National Oceanic and Atmospheric Administration, And I'm sure they have physics equation relating altitude to air temperature, taking into account air currents and moisture and sun's radiation and all that good stuff. And then you could probably project what it would be, run the equations, and then get, oh, Mount Everest, this is probably what the temperature is going to be, so I get prepared for it. Or what if, I'm not saying we can do it, but what if we could construct a causal model from just these measurements? There is relationship, so if we can abstract what is causing what, we are going to be in a good shape in using that from actual measured data rather than physics. Now, I can tell you that causality is a rather slippery concept. So let's start with simple stuff so we can make some sense of it. So we have this little cartoon here where a truck, a dead truck, two people are pushing. We obviously know what is causing the truck to be moving, not this guy who's standing in the bed of the truck. So correlation causation is nicely, well separated in this case. Now, if you just look at the basics, so if you have two things, so it's like a person and the truck, two variables, correlation is a single relationship. And actually, correlation has no direction. When we say X causes Y, that's a wrong statement or incorrect statement. It is X and Y are correlated. That's all you can say. However, when we are talking about causation between two things, the blue and the green, and here's my usual joke, if it's a dog and there's a man, the direction makes big difference. Dog bites man, it's not a news item. Man bites dog, much bigger news item, it will be front page. Right? So direction really matters, and there could be no cause between the two also. So studying this, we need some basic definitions, and without complicating it a lot, an engineering operational definition is X causes Y. When X changes, Y changes. You have to hold all the others constant and all that good stuff. So this is our simple definition. Along with causation, there is a word which is relatively unfamiliar to most people. It's called counterfactual. Counterfactual, you can read what is written there. That example, you're not going to go cut off kangaroos' tails to see if they will topple over, right? So your ability to think of things that didn't actually happen, but in your mind you can think about it uh, and analyze what could, what can or can't happen. That's the title of Marletto's new book, 2021. She's a theoretical physicist in Cambridge, and she says she is reformulating the entire theoretical physics, quantum mechanics, gravity, all of that, using this concept of counterfactuals. So way beyond my pay scale, but it looks like this is serious effort on her part. So our main focus is on what is called causal inference. That is, from observational data, find out how the data is being generated. So in the altitude temperature case, from all those measurements, what we want to find is what is generating from altitude these temperatures. So if you're able to find that, we can predict for Mount Everest temperature, right? So this is different from experimental or interventional data. In medicine, you do randomized control trials, right? One group, you give meds, the other group, placebo. So that's interventional. Many of those experiments are just not possible or practical for many IoT applications on the plant floor. A lot of those things just cannot be done. So what we are after is data generating model, and that's called the causal model. Now, a favorite way to think about that would be it's a mechanism. What is the mechanism that's generating the data? I talked about brain earlier. What is the mechanism inside the brain that is showing you the so-called EEG, electroencephalogram, on the surface? So mechanism, once you have it in hand, the ability is to do what is called counterfactual experiments. We'll be talking more about it, so-called what-if analysis. So without actually doing interventions on the plant floor, with these mechanisms or causal model, we can do what if analysis, performance improvement questions, root cause analysis, and so on. That is the power of this whole method. So the takeaway is what we want is the data generating model, which we call a causal model, which think of it as a mechanism. So much work has happened in this area. In fact, since 2000, two Nobel Prizes were awarded for causality in economics. One this year, actually. Randomized control trials to establish cause effect for meds has been ongoing forever. In 1980s, there was some very interesting work in what is called blind signal separation or blind channel equalization in telecom. So there's good history. And since mid 2000, some powerful estimation methods for causal parameters, such as independent component analysis, has become available. So we have a good tool chest to go forward for causality in IoT. So in causality or any machine learning, so-called AI in IoT, the way I think of it is housed in digital twin. Right? And this is my definition of digital twin. The basics are getting the data, sensors, connectivity, and bringing it into some nice platform and so on. But the digital twin performs three big major functions: condition monitoring and assessment, root cause analysis, and you close the loop through visualization. So these three functions are performed through simple threshold analysis or some basic machine learning, etc. And then let me jump to the closing the loop. This is the dashboard, as simple as this thing. It could be 3D, AR, VR coming. They may actually be closing the loop in some sort of closed loop control, automated plants, and so on. So the middle part is what I call causal digital twin. This is where we talk about simulation, what if analysis, that is actually simulation. So there are many methods I had indicated, Noah's physics models you can use, just if then else, the old expert system kind of things can be used. And this is where causal models and the methods we develop also reside. Now, it should be noted that every digital twin does not need this causal digital twin component. This is a diagram from AWS. Amazon has a very reasonable, and lots of others, simple, what we call a ladder of digital twins, starting from just plain descriptive, going all the way to this living is really the three blocks together, including causal digital twin. So there is no, one could simply start with collecting the data and showing it on a dashboard. That's a perfectly all right start to have. But you need to move up the ladder to go beyond that trough of disillusionment and getting to the other side. That is the takeaway from this slide. Now let us see, if we had that causal digital twin, what would be a compelling use case? There are many, but this is one of my favorite. As you know, your Tesla probably has all these sensors going on, sensor on the battery for the current draw, torque meter on the motor, RPM measurement of the tire rotation, and so on and so forth. Now, if you don't combine them, you're looking at it as if you're looking through straws. There's a human medical condition called Usher syndrome. It's like you only see a little narrow view. So you don't see the full picture. If you see the full picture, in this case, some amazing things can be done. Maybe, Elon Musk is already doing it. I don't know. But you could actually, the compelling objective of in EV would be maximizing the driving range, right? So if you looked at only A or B or C or them separately, you probably won't be able to find the full picture so that you can maximize the driving range to the maximum. The reason for that is you have to do it in real time, because my driving style may be different from my wife's if she's driving the same car. One day I'm driving on this road, the another day I'm driving on another road. Driving conditions are different. So if that causal digital twin is running in this car, you'll be able to optimize the conditions so that the driving range is maximized in real time under the existing conditions. Of course, there will be a factory setting where they have looked across many cars and aggregated the information, and there are some set points. But here, the set points are could be adjusted on the fly so that you get the maximum range. So let this be the motivation for what we're going to do with causality in IoT. So I think of it as a generic multi-channel IoT causal digital twin. That is what we want to end up with, and that's what we will end up with at the end of this talk. Now, this is really not just for automotive. You can see this being applied for industrial, health tech, consumer, building, smart city. You have cameras from various street corners, and some video analytics tell you traffic flow. So that'll be like A, B, C, etc. But when you see the big picture, various optimizations and traffic engineering can be implemented. So wherever there is multi-channel sensor data, MIC digital twin is applicable. So it really is a horizontal technology. Now let us look at what exactly is causality. Now comes the fun part. Let's really understand what causality is. It's, as I said, a slippery topic. It's a broad topic, but it has been applied over the last 2 decades and a little bit more in econometrics, health sciences, social sciences. So what I have done is simply corral all these works and make it applicable to IoT and added some original component from Calvin filtering in that work. But in the discussion from here on, we'll focus specifically on this MIC digital twin that we talked about, so that we can keep it focused and not get into philosophical issues related to causality. This slide is more for people who have heard about causality and have some knowledge of it. So this is just something to keep in mind so that they can kind of fix what I'm talking about within their mental model. So starting, and the most common one is Judaic Pearl is a name, this so-called Bayesian networks. Again, been around for two decades. They're mainly useful for what's called survey type data. Technically, the data is independent and identically distributed. So the simple way to think about it is, let's say Procter & Gamble introduces a new soap, and when you come and walk out of the store, there is somebody with a clipboard asking you survey questions. Their columns, color, smell, price, etc. And then your subject 1, 2, 3 up to 1,000,000, 500,000, whatever. So they would collect from all of these, rated 1 to 10. So each of the rows, are independent people's independent opinion. So they are IID. That's where this is useful. When it is not, these techniques cannot be applied. And as you already know, or you will soon when we discuss in MIC, it's really multi-channel data time series, like in the electric EV we talked about. It is continuous measurement of battery drain and so on. Those are all time series, and they are all correlated. So they're actually, in each of the columns are those A, B, and C. So they're not, each of the rows are not identically distributed because they are autocorrelated. So those techniques cannot be used. There is a generic model in between called structural equation model. So these are, so in some cases, especially in econometrics, you can make up parametric equations. So this may also be the case where there are physics-based equations available, such as, again, NOAA supplies you with the equation for altitude and temperature, etc. What we will be focusing on, and what is most applicable to MIC digital twin, is the so-called structural causal model, and it uses a specific non-parametric model called SVAR. The details are not necessary in this talk because I'm not going to go to those depth That's another advanced conversation. It's a structural vector autoregressive model is what is used. So these are time series data and stochastic estimation methods are used in this case. So let us get to the nitty gritty of causality. What exactly is causality? As you will see, the problem with causality is that it does not have a simple definition like, let's say, in Shannon information. There is actually a definition, a nice compact definition based on probability density function, and there is a unit, bits. There is nothing like that for causality. That's what it makes a little tricky. So let's revisit our truck a little bit carefully. But first, let me mention correlation is what we'll call an epiphenomena. So epiphenomena are secondary phenomena. Go to that brain example again. It is actually the neurons firing inside the brain that is causing the electroencephalogram, EEG. So EEG is an epiphenomenon. So that's what you're measuring. So in many cases, that's what we are measuring. It is the outside or surface measurements. What is inside is the mechanism that we want to get at. Because if we know the mechanism, we are going to be able to say what will be, then we can change the mechanism, the coupling between various sources in the brain, for example, through drugs or electric stimulation, magnetic stimulation, and then EEG will show its various differences. So we really want to understand back to the mechanism that is underlying the thing. So let's come back to our pushing guy, the truck. So clearly, A is the one who's causing the truck to move, in his pushing. And you can always absolutely say, because he's pushing and this is moving, he's correlated with truck movement. By the way, this guy's pushing is also correlated, but that's the second story, focusing on A. So A causes the truck movement, and A is correlated with the truck movement. So you can make this not a very useful statement, but a statement saying there is no causation without correlation. If you're causing something, you will be correlated. But what that allows us to say is, in that case, causation is correlation plus something else. So there's always correlation, like in both cases, difference between A and B. A have something in addition to it. So what is that? The correlation plus something else is causation. So we ask, what is that? Now, how much correlation is implied by causation? So if A is causing the truck to move by causation, is the correlation between A and movement 1? Well, it need not be, right? Truck could move because as just when he was pushing, there was like a strong gust of wind in the proper direction. So it need not be. But let's assume there are no other associations other than A is pushing, right? Then the correlation is 1 between A and. So if you drew a little picture like we used to in early statistics course between X, that is pushing, and Y, that is the movement, and these are the data points as it moves. When these red measured points are strictly on a straight line, that is correlation equal to 1. If it is less than 1, it'll be above and below the blue dotted line. So correlation is equal to 1 when causation is the cause, so to speak. Pushing is the cause in this case. So you could say the causal factor from this picture is the regression coefficient between pushing and movement. Because if this is causing this, and based on, if you push this much, it'll move this much, the slope is the correlation, is the regression coefficient between pushing and movement. And that is the causal, that is defined as the causal factor. Now we can see whether this will get into trouble, etc. But we will see that under certain set of assumptions that ceases to be the case. So we said causal factor is the regression coefficient, right? We'll have to wrap it with a few more assumptions. This is true if one acyclic. So from graph theory folks, there are acyclic graphs This is kind of well known. If you're a matrix guy, this will correspond to uh, adjacency matrix, or in this case, we call it mixing matrix, is strictly triangular. But in common parlance, what it means is there is no back and forth effect between the truck and the guys, right? Trucking movement is not going to cause anything to the guys, right? So there is no cyclicity. The second thing is called Markov condition. That is, there is the causal relations is strictly the only thing between the variables. So, for example, there isn't a gust of wind outside that is coming and causing the causal relationship. It is captured in the picture, so to speak, in the graph. Faithfulness is the third assumption required. It's not strictly required, it appears. Uh, so there are no coincidental cancellations. So it is like, there is a guy on the other side of the truck we cannot see who's pushing in the other direction. So those kind of strange situations, this model cannot handle. So under these assumptions, causal factor is the regression coefficient. Now we're going to find the model. We talked about SVAR and identify the regression coefficients there and then relate them to causal factors. So to do that first, let's look at this is just a picture of how the data would look like for multi-channel data collection. So these are many channels of data. So this would be in the EV case, a battery drain, torque, RPM, and this is continuously measured. So this is the current instant. It's kind of drawn backwards because usually it'll look the other way, but for a particular reason. So this is the current instant of time. This is the data from last measurements instant. This is the one before. This is the one many before. Right? So what we are trying to do, what we want to find is all these causal relationships. So if you want to know the current draw that is at this point, how is it being causally affected by the other variables at the current instant of time? Immediately, it's like a snapshot. They are called structural causality or structural causal factors. Now, your current draw at this instant will also be affected by past. Right? It'll be affected by the past. It could be past millisecond when the data is being, off the RPM, for example. So the past also affects these things. In our in causality directed acyclic graph under the assumptions, we don't look at two things. We don't look at things that are called self-causation. So there is no arrow that goes from this point back to that point. None of these arrows are bidirectional. That is the part of the assumption we made. And the same thing here. For the past, we also don't consider the same channel's past effect because these things will also be connected to this. We will come to something called Granger causality. Granger was the one who won Nobel Prize in economics back in 2002 or 4 or something. So these are the type of causality. You can think of Granger causality as delayed or lagged causality, and this as structural or instantaneous causality. The way it is captured in an equation is that SVAR we talked about. So those who are comfortable with it can see the current measurement. Yt is a vector, so these are all these data points. It's all written together as a multi-variable stochastic process, not one at a time, so it looks kind of funny if you're not used to it. But the blue arrows are these S0 matrices. This is the structural causality. And SD matrix is this lagged causal factors or Granger causality. Now, we said a few things such as there is no self-causality, which some of you this may make immediate sense. That would mean that S0 matrix diagonal elements are 0. If that didn't make immediate sense, that's okay. Now, this is not enough. And again, we'll see why in the next slide or two. You need an additional assumption. In this model, this is linear. The ET, the unmeasured, the noise in the system, it has to be non-Gaussian and it has to be independent. That is, the noise in this channel, this channel, this channel are independent. It's like any mathematical approach, any statistical probabilistic approach. You had to make certain assumptions. Based on that, you can make estimates. And if the estimates are good enough that you can live with, that is sufficient. So this type of model is called lingam, linear non-Gaussian acyclic model. So if these three, acyclic, Markov, and faithful, and for this particular model, it is lingam, we can estimate structural causal factors and lagged causal factors. Pretty simply. Well, it takes a lot of calculation, but it's just algorithm. Now, I have to say that through this first pass, this is not easy. Hard to unpack this. Why is acyclic, Markov, and faithful make it causal? Why does the noise has to be non-Gaussian independent? And then only regression parameters are the causal parameters. So there is a lot to be unpacked. So I agree, it's a little dazed, first time. So why are model parameters the same as causal factors? It's not obvious. What are all these assumptions doing here, and why are they necessary? This has to be a more detailed technical talk. So those who are interested can invite me to address that, but you have to be really ready to do some interesting discussion. So, but it's useful, that deeper discussion, because when you have deeper understanding of causality, you'll apply it appropriately in digital twin situations. So I strongly recommend that. But now we are going to stop with assumptions and move forward in simple ways and talk about IoT application cases. So since the math of SFAR estimation is a little complicated, and the lingam and so on, I'm going to use more of a story to explain how that is done to a surface level. There is a lot more deep depth, but I'll try to hit on the interesting points. Let's focus on this picture on the top. This is something, a well-known effect called cocktail party problem. It is also, by the way, I mentioned something called blind signal separation, blind source separation, blind channel equalization. These are all cocktail party. So the cocktail party problem is this. This is a room. The blue is the dividing wall between two rooms. Two people are speaking simultaneously, and there are two speakers picking, because there is no separation between them, picking up both conversation. And these mixed signals, X1 and X2, is available on this other room, and someone is trying to listen. And because they are talking over each other, it's hard to figure out. So can you process it somehow so that you can separate, and then Y1 is a good estimate of S1 and Y2 is a good estimate of S2, right? So the matrix way in which you write this is, so the data that you get, this X1, X2, is some mixing matrix. So A, B, C, D are the elements of that mixing matrix, times S, these signals, right? Now, if you look at this, I mean, there's a matrix equation, but forget that for the moment. Just think of it, and it's also, stochastic equation. But forget this is, let's say it's deterministic scalar quantities, X equal to AS. If I said, okay, X is 10, tell me what A and S are, you're going to say, get out of here. Makes no sense, right? A could be 1, S could be 10, then X is 10. A could be 1 upon 10 and S could be 100, then this is also 10. There's infinite answers. These are so-called field-conditioned problems, which are impossible to solve. Now, what these guys, the blind signal separation guys, and later what they figured out is that, well, under certain conditions, we'll see under lingam conditions, they can indeed be separated, and y would be a good solution or estimate of S1. That is what is shown here. It's a little complex, but I'll go through quickly. So this is the actual speech. This is where they are interacting with each other. So this is x1, x2. This is what you get on the other side. So through this processing, I'll just call it ICA, dependent component analysis, you actually are able to separate and get the old speech back. Now, in doing that, these two, the S's have certain property. They are non-Gaussian and independent. Independence is a big deal because non-Gaussian comes because if it is Gaussian, uncorrelated is equal to independent. There is no way to separate. Independence condition cannot be imposed on Gaussian data because it's the same as uncorrelated. Uncorrelated cannot solve this problem. So that is why, because we use independence to separate the two and get y1 and y2 to be as close to s1 and s2 as possible, that they have to be non-Gaussian. And this is the methodology ICA that does it. Now, this equation is very similar to our Lingam model. You know, in SVAR, there was YT, and then there were two terms plus noise, right? The second term there is called vector autoregressive, VAR. VAR is well known, we know how to do it. It is the first part, the structural causality factors, that S0, that is hard to solve. So here we are looking at only that. So this equation of the structural equation part of the Lingam model is the same as this x equal to as, y equal to be. So this solution, this method, works for solving Lingam models. So let's remind ourselves the multi-channel IoT data layout. As we said, these are from various sensors. This is time is flowing this way at this instant of time, current time. This is the data value of channel 1, data value channel 2, channel 2. So this is actually some waveform, right? I'm just showing that point. So the current instantaneous causation is called structural causality. Delayed causation is called Granger causality. That is, past other channels can affect my current channel of interest. So here we are focusing on channel 1. We will do the same thing with channel 2, channel 3, so on. So this is just for our current channels. So with all the tools that we have developed, or tested it on bearing vibration data from NASA. This is a well-known and well-established data. There are 4 bearings that are run to failure from pristine day 1 to what I call D-Day. It took about 2 weeks, and on that day, D-Day, B1 kind of failed. So this data is a nice one to process. So the corresponding structural and Granger causality is shown here. Just a quick comment on this Granger causality. So Granger causality, as Granger defined in the Nobel Prize work, is 1. This is a generalized version of Granger causality, but the same sense. And in SVAR model, so he had only that structural causal, he did not have the structural causal part, and for that we had to make a correction to his Granger. So it's corrected, generalized Granger causal factor. But anyway, on D-Day, B1 failed, this is the one. So you can see there is a strong positive causal something going on from B2, that is from this to B1. There is also something else going on from in the past. So notice that we would show the current and the past. The current instant t is repeated twice, and then it's t minus 1. Then t minus 2 will be here, t minus 3 here, etc., etc. I'll show you in another picture, trying not to confuse it here. So you see these causal relationships. So a machine dynamicist or a mechanic will be able to make sense of it. So this kind of picture is what I'm calling fence causal graph. Now this is the UI UX for causal digital twin. To me, this is the digital twin. In many dashboards, you could probably overlay this on a nice picture of bearing and the actual test setup in this case. That may make a good UI, but essentially This is a graph and drawn this way as a ladder. Now, this may be unfamiliar to a lot of people, so you can draw it like the regular. This is what a DAG graph plots usually would be. But for us, that is not enough because you can only show the instantaneous one. We can't show the lagged one. So to do the lagged one, you can probably show this is one, and you can have more like this. To me, it's too complex. So this is the UI UX that I have settled on for now. And some of you who may get involved in this, I'm sure will come up with some much better UI UX for this work. So this is the same fence diagram. Now I've actually written down the actual causal factors. As a positive factor, in my UI, dotted line is negative, blue is structural, green is Granger, and so on. Now, in my book that you probably saw in the second slide that's published, I talk about it as an inverse modeling problem. And earlier on, I talked about, measuring brain signals from the surface of the brain. So this is like EEG measurement. And these are like various, modules in the brain underneath. And as this coupling or these causal factors, so I'm interchangeably using coupling and causality, causal factors, the data that you measure will be different. So our problem has been from that data, can you tell, oh, this is like an epileptic focus and the coupling suddenly increased and that's why there is a seizure happening and things like that. So I've always been fascinated by this kind of a model surface and then what's happening underneath. So I just want to talk about another UI kind of idea. But first, just to be clear, to do simulation with this, you had to rearrange the equation because on the left-hand side, you can only have the current time t. So everything here is delayed. Of course, this is to be obtained from the actual modeling ET. So with that simulation equation, I'm just reproducing the surface structure, deep structure picture below. This is how an engineer would look like. We would call it an engineering process diagram or something. So on the surface, there are 4 bearings. So all these connections, these are exactly, this flowchart is exactly this fence diagram. So ET goes as input and these things, and they're coupling back. And this is just another way to do it. Maybe in machinery, IoT, digital twin, this would be the UI and not that. But just a different way of thinking and looking at it. Now you would be curious what happened or what does the uh, fence diagram digital twin look over time. February 12th, that was the pristine day as I talked about. February 19th is the D-Day when bearing 1 died. And you can clearly see, the pristine, everything, there's hardly any coupling. They're all like nicely bearings rotating by themselves and not, shaft is not bent and it's not affecting each other. The day before D-Day, things are starting to get worse, and D-Day, this thing happens. Like I said, I mean, even, like 3 instances before, it has some effect on this bearing. So typically a machine designer would look at it and say, oh, this shows that the shaft is bent and then is flexing or something. So that's a domain experts area that we need to bring in. Now we had mentioned the real power of causal digital twin is counterfactual experiments, what if analysis, etc. So let's look at my engineering flowchart type of digital twin again. So the real value is this. You see these weights. So once we estimated this from that, say you take February 19th data. So you have weights, actual values that you got for these things. You have the actual estimated noise in it. So you can actually run this simulation and get exact same data. But the idea is that this domain expert can now come and knowing how this is affecting the various mechanical parts, he can play around with these knobs. He can increase the coupling, decrease the coupling, and see and keep B1 from fraying, right, or getting fried. So this is the power of this. And once you find that may go back into the design of that bearing system. Now, instead of this bearing, this is something else, a much bigger, let's say, well, that automotive case, these are A, B, and C data. This is the set point that the Tesla car, while you're driving to your driving style and the road conditions, will automatically change and adjust. In a smart city case, when you have video analytics of various things, there may be some adjustments you can do to traffic lights so that congestion can be avoided, etc. So this the real power of all of this is these castle, the what if analysis by turning these knobs and finding the set points to achieve the business goals that you have. Now we'll take a quick look at actual implementation of this. How would this work? Uh, Causal digital twin or causal machine learning in this case. So 3 use cases could be a patient in an ICU. This is those multi-channel data coming from them. Or this could be an industrial plant, or it could be smart city. So our objective is get these multi-channel data from any of these cases. So the flow would go like this. So that's that YT of the SFAR model. And here there is the estimation method has 4 steps. It uses independent component analysis. They have added some Kalman filtering to estimate the structural causal factors, range of causal factors, and the noise in the system. Now, as we said, it has to satisfy the Lingam uh, assumptions, and that's pretty critical. So kurtosis test will show that whether it's Gaussian or non-Gaussian. If it is Gaussian, you cannot proceed. If it is non-Gaussian, and you have to make sure they are independent, that's noise for each of these channels are independent. So these turns out there is theoretical arguments behind it and practical, and including for the bearing data, I did these tests, and they're indeed non-Gaussian and independent. It is applicable fairly widely, right? So this is where you have to test in each of these cases. You can't. It's not a very simple time series analysis. You got to be much more careful. And this is our digital twin, if you will. So what we are doing is we will supply all those factors into this our digital twin, and the workflow will be where domain expert will come and turn the knobs and find set points, and then probably, I mean, I've actually done that where this is that B1 bearing data where it's much larger. I don't know whether you can see it, but by setting some weights, that has become like pristine. It's not showing any of those break activities. So how do you put this all on a software stack, and how does this get implemented? So this is a quick upper level view of that. The next slide. So in general, step back, my thinking is there is more than 2 ways to, in fact 3 probably, is to infuse AI like digital twin and so on into IoT use cases. One is for predictive analytics, one is for prescriptive analytics. So this is where our causal digital twin lives. This is where more of this old statistical machine learning digital twin lives. I also believe that expert system, like if this is a medical doctor, his knowledge or her knowledge, and using his if then else flow chart, we should produce results and compare it to with automated methods so that you can build up that person's confidence in our solution. But this only comes to the first part of that IoT curve I predicted. And with uh, causal digital twin, we'll go to the next step of optimizing and so on. Stack basically would look like the edge, the data is getting collected, it comes into your basic in the cloud machine learning IoT stack. The top of the stack is more of the higher order functions. Machine learning may sit here. A causal engine probably would be a separate engine with APIs exposed that you call. So the workflow would look something like this in the usage. So data will come from the edge, and that data then, the first time it comes, it'll call the causal digital twin API, and discover the causal structure, that is the graph from here. Or there is another case where sometimes a domain expert can actually sketch the graph, what is connected to what. The weights may not be known, but the graph structure discovery can be aided by the domain expert's actual input. And then the rest of it would be estimation using our SVAR method, your MIC digital twin. And the way it is typically used is, in one way, of course, you can use causal factors to detect a fault, right? But really, that's an overkill. There are very simple threshold methods. But if you want, you can do that and deploy that at the edge. But typically, it'll be sitting in the cloud and in the central location where, when there is a fault, we'll do root cause analysis. Or you do maybe quarterly or something, you do an analysis about how to improve certain process performance, reduce waste, etc. So that would be the use case, which is what I'm trying to show here. From this is actually a picture from my Rockwell Automation digital twin visualization. These are the various measurement points. So typically it is done with simple methods at the edge of detecting whether there is a problem, temperature has exceeded a threshold or something. And you could also use machine learning and causality techniques. But the big work goes on in the cloud, where the causal analysis is done for what if analysis. So I'll close with where things are. It's been a significant amount of work that has happened in the last 5 years. There is almost an acceleration of work in this area. And the very interesting part is machine learning folks have taken this seriously. And I will draw your attention to Sholkoff's work. This is a publication, couldn't be hotter than this. April 2022, it's a pre-publication, large, the most authoritative, most recent, and I think the most excellent. So this is a person and his students. There's another guy called Muij in the University in Netherlands somewhere. Their work is outstanding work. There is another group, Comon, COMON, in France, in Sofia Antipolis. There is Haivarinen in Helsinki, who developed ICA, independent component analysis. So there is significant amount of work. There is Judea Pro and Spurts and Carnegie Mellon work going on. But this is the state of the art. Bernard makes the point that you need causality to get models that support intervention planning and reasoning. So these are the things we talk about, root cause analysis, performance improvement. And he has laid out beautifully the framework for this thing. There's nothing dramatically new beyond what I said in those models, but it is bringing it all together in a very beautiful way. And I would pull this all together with this one picture. So really, there is a hierarchy here. So in this triangle, if it is simply fault detection, just use deterministic ML. Don't even have to, maybe it's algebraic ML, because this fault detection is typically usually you set a threshold. If it exceeds, set off an alarm, right? Very simple. Fault prediction requires some more, maybe some time series analysis and prediction. So you need statistical methods. But the high value item in IoT, fault understanding and improvement, to take you beyond that chasm I talked about, we need causal machine learning. So of course you can use it for other purposes, but that would be rather foolish. So this is the current state of where we are. Beyond this video, these are my contributions that are available in the public domain. There's a foundational expository article, much more technical, in that first bullet. The paper is available there. All the algorithms have been fully debugged and tested. I'm actually willing to give up or work with my free MATLAB code and even hand holding if there are serious POCs. When I say serious, what I mean is for significant use cases, not toy problems, with lots of multi-channel data. That's all in any domain. It would be wonderful to try it out. And I would also want a real interest in your org. These are not things where you can do it as a one-man basis. So I would want to see a groundswell of interest, and I'll be happy to handhold and take you through this. There is another video from some time ago that I think is probably superseded by this one. That has more details on the counterfactual experiments. I explained 2 or 3 instances in that. I hope you had as much fun as I did talking about causality. Causal machine learning and causal digital twin are going to be significantly important in the coming years. And the reason is that is how you address high value problems in IoT, what if analysis, performance improvement. So I hope you all take a serious interest and do a lot with causal digital twins. Thank you very much for your attention.